Hey scholars, this is Mrs. Gregerson, and I am just trying to get some videos done here for you guys to have us back up there on Academy Central. I just want to say I'm very proud of my students. You guys are a very talented group of kids who amaze me with what you do here with athletics, fine arts, visual, vocal, instrumental, how you guys serve the community. I'm overwhelmed by you. And so this is a short, sweet lesson, so I thought, hey, I'd put that in there. But I want you to know I'm very proud. It's a great honor to see what God gives you guys as talents and to be a small part of that. It's pretty cool. So today we're actually still in chapter 8. We're talking about similarity. And remember with similarity, we had the angle-angle similarity for triangles. We had the side-angle-side similarity and side-side-side. And everything has to match up because the corresponding angles are congruent and the corresponding sides are proportional, which means the similarity ratios are equal. Now, the cool thing is, because of those things, we can sometimes take shortcuts. Kind of like what we did with the geometric means when we did the snail and when we did the arrows through the middle. And so when we did that, we were really just matching up corresponding sides, but it kept us from having to really muddle through the mess to figure out which ones correspond. Well, today we have one that has a cool name. It's called the side splitter theorem. And we actually used something like this in the past. And I want you to go back the other day to class. Now, before, we had a theorem that said, when I had 3 or more parallel lines, and they were, and if they intersected a transversal into congruent parts, I knew if any other transversal would have to be divided into congruent parts. And they would all be that way. Well, this one takes a just slightly different approach, but it's the same idea. It's if I have parallel lines that divides, you're going to divide something proportionally because those parallel lines are going to divide it the same way. Now, the only difference is in this diagram, I'm going to just draw a parallel line on top. And so we're using that type of concept, but all of this can be proven using similar triangles. So that's the cool part behind it, is because they're similar, this works. So let's fill in our theorem. It's called the side splitter theorem. So what do you think that line is doing to the sides? That's right, splitting it. Kind of cool, isn't it? So here we go. If a line parallel to a side of a triangle, so we're parallel to the side of a triangle, so right here, intersects the other two sides, then it divides the two sides proportionally. So basically I can, set up a proportion to solve for what's missing. Now here's the cool thing. It's very easy to do. So here they tell us that we have our triangle. EF is parallel. So that means that AE goes to, now, and it really doesn't matter how you do this. There's more than one way. Some people go like this. AE is to EB, and they go top is to bottom here, as AF is to FC, which is kind of how I do it. Or you can match it across. You literally could go, and I'm going to use the alternate one here, go across this way, which is an easy kind of way of doing it as long as you go the same direction. AE is to AF as BE is to FC. And you notice really all that we did was switch our means, yeah, excuse me, I'm about to call them extremes. Yeah, we switched our means. So it's really the same proportions how you want to do it. Do I want to go top is to bottom, or do I want to go across? Either way, you're going to set up a proportion. It's really simple to do. Now before, we had to use similar triangles to do this. And so here we had to find the length of segment US. We would have had to go 14 is to 14 plus x as 10 is to 14. Well, we don't have to do that anymore. Now we can just set up a quick proportion. I can go 14 is to x as 10 is to 4. Now if you want to go ahead and reduce, that's great. So you get 14 is to x as 5 is to 2. Cross multiply, 5x equals 2 times 14. So we get 5x is equal to 28, divide by 5. X is going to be 28 over 5. Now notice, what if I wanted to go across? Let's say I wanted to go like this. I could go 14 is to 10 as x is to 4. And if you notice, you know, I just realized, did I? Yeah. I'm going to just sit there and simplify. Sorry, totally messing up here. We get here 7/5 is x to 4. And when you cross multiply, you get 5x equals 4 times 7. Oh look, 5x is equal to 28. X is still going to be 28 over 5. Now, I kind of prefer using, like I said, top is to bottom when I do these, but notice I get the same answer if I go across. I'm matching which parts are going to be divided by the parallel lines. It's not too difficult. Now, if we were in class, I'd say, okay, your turn. Mark what's missing. And they say, look for the length of segment PN. And please remember, when there's no bar over the top, we're meaning length. That is just not acceptable anymore if you don't understand what those two letters stand for anymore. So we have to make sure it's the length of segment PN. Now, looking at that, I'm given my parallel line, so that's kind of my clue. So then you would have to decide what proportion you want to set it up. And I'm just going to go this way. 3 is to x as 2 is to 5. Or you could go, you know, and the same thing here. You could also, and I've done this before, x is to 3 as 5 is to 2. In fact, in my written notes, that's how I have it. So it doesn't really matter either way. So then when you cross multiply, you get 2 times x equals 3 times 5. 2x is equal to 15. X is equal to 15 over 2. So we're pretty excited about that. Hopefully that kind of gives you an idea on this one. Now, the next one is really how it's kind of related up here. Is really also down here too. It's the 2 transversal proportionality. And really what it's saying is, hey, guess what? Just like when I have the parallel lines here with the triangles, I'm going to divide things up proportionally. So how the triangle, because all we have to do is add the line here, it really means exactly the same thing down here. I'm going to divide it up proportionally. So let's write it down here. If 3 or more parallel lines intersect 2 transversals, then they divide the transversals proportionally. Okay? So what they're saying is these two sides are going to correspond because we have our parallel lines, and I know these two sides are going to correspond. So you can do it kind of like the same way that we did before, and I really, quite frankly, it goes either way. Let's say I went across, just like you saw those two segments. So if I go across, I go AC is to BD, but I have to make sure I go the same direction. So if it's AC to BD, I'm going to have to go CE is going to be to DF, or if you're doing that, I could go top is to bottom. And I kind of like that one. AC is to CE as, and now if I go top to bottom again, BD is to DF. Now, again, I'm using slang to understand this, but I'm just sitting there putting the correspondence together so we can make sure we can calculate these. So here we have our 3 parallel lines or segments here, because I didn't put arrows on, so I'll put arrows to make me feel better. Okay. Now, if I'm doing this, I treat it like the triangle. Those are parallel. I know these are being divided proportionally. The easiest way for me to do it is like the bottom one that we did over here. 16 is to x as 14 is to 21. Now, the cool thing is, please go ahead and reduce. It sure makes your life a lot easier. I'm going to change to a blue pen here. 7 can come out of both, so we get 2 is to 3. I'm going to cross multiply. So I get 2 times x equals 16 times 3. So 2x is equal to 48. Divide by 2. X is equal to 24. And when you think about it, if that's 24, it kind of proportionally makes sense. Those two are the smaller ones. These two should be the larger ones. And 16 is a little bit larger than 14, so 24 is a little bit larger than 21. It gives you a common sense approach. Guys, that's one thing as good mathematicians we need to practice. We need to practice thinking, does this logically make sense? All right, so we're going to go and flip the page, and we're going to apply this one more time, and then we're going to turn around and do one more theorem.